Thanks a lot. Thanks a lot, Jared, and thanks for having me. It turns out there's actually a PyData conference going on right now in Dallas. So I don't know what that says about me, but the last time I was at an R conference, I wasn't speaking, but it was the R in Finance conference, and I've got to say that after about half the conference, I started to feel really self-conscious about not being German. If you've ever been to R in Finance, I mean, you'll understand. So necessary disclaimer that this is what I think. So now that I work for a bigger company, I got to make sure sort of to disclaim when I'm expressing strong opinions, which I very frequently do. So the goal of this talk, and it's a lot for 20 minutes, but I wanted to talk generally about DataFrame interfaces as they which are one of the primary tools that we use. Present some strong opinions, some of which are perhaps not as well formed as they ought to be, just to sort of share some of my thoughts and experiences from building DataFrames over the last 7 years or so. I will point out that it is a very nuanced discussion, and it's far too nuanced for 20 minutes. So some of the I won't necessarily present some of these things as fact or fully finalized conclusions. So these are things that we could debate for hours and hours and hours, but just some food for thought. What have I been doing with myself the last number of years? I started working on Pandas. I worked for AQR up in Greenwich, Connecticut for about 3 years. Got really frustrated with R. And I was excited about Python. I'm like, look, there's no DataFrames here. There's really not any good data wrangling tools. Oh yeah, we've got a book there. So I started on this journey at the beginning of 2008, building Pandas, and that led me to get involved in the open source community and write a book and do lots of things. And now it's suddenly 2015. I took a few years off from honest employment, went back to grad school, dropped out of grad school, came back here, did a lot of open source, wrote a book. Things happen, I guess, in your career. So I guess the question for this talk is, what's in a data frame? A table with some rows by any other name would analyze as sweet. Or putting it a different way, perhaps, is if you've got a table, why not put a data frame interface on it? So when I talk about data frames, I don't need to tell you, being R programmers, that you have a table and a data frame is just sort of a concept of some kind of interface for working with tabular data. And unfortunately, it goes pretty far beyond the data structure itself and has a lot to do with the API and how you think about expressing computation on the data, and has all of the hooks into your modeling frameworks, how you do run linear regressions, how you describe, essentially how you build models. So, when you talk about data frames, you got to sort of focus the discussion on what aspects of the data frame. Is it the data structure itself? Is it the sort of data tidying, data wrangling interfaces? Is it the modeling interface? Is it the relational algebra? Is it how you're reading data from CSV files or dealing with databases? So unfortunately, that's why the data frame discussion ends up devolving into this fixation on one topic or another. And there's lots of different ways that you can compare them to each other. And I made this kind of non-exhaustive list of all the things that you can find in any particular suite of data frame tools. And the list goes on down to the floor. All the ways that you can run benchmarks, so you can compare APIs and be like, well, look, it's easier to do this one weird trick here than it is to do over here, and this code runs faster here versus here, and it kind of gets into this little shooting match, and it's like, well, what is the point? Why do we care? And there's a kind of a macro trend that I see going on, and it's 2015, and I spent a lot of time thinking about what's going to happen in 10 years. So you look 10 years ago, what were we doing 10 years ago? We didn't have very nice IDEs. We didn't have very good libraries. Most of the stuff that Hadley Wickham has built didn't exist in 2005. There was still R, there was still Python, but it was a very different time. And so if you look 10 years into the future, what is that going to look like? And my hypothesis, and we'll see if this ends up actually being true. So I guess the trick to sort of looking really smart is to make a lot of predictions, and some of them will end up being true, and you just talk about those. So, but I've already seen what I described here happening, which is that the how we're storing data, how we're performing computations on it, and then how we're sort of thinking about those computations and kind of the user interface, which, user interface means a lot of things to different people, but like the API and like the code that you're writing, that's your user interface as a programmer, is that I think in 10 years that these are all going to become decoupled, and we're going to have really great distributed data storage systems, really fast, interactive, scalable computation engines. And for us as programmers, whether it's R, Python, kind of whatever data science language, the challenge is going to be, can we build really great user interfaces? And there's a lot of reasons why you want other people to assume kind of the storage and execution problem. It would be really nice if rather than kind of comparing benchmarks between data table, dplyr, and pandas, we say, well, why aren't these all using the same code base? Why should there be multiple implementations of joins and filters and aggregations and all of that data munging stuff? There's ways that we could work together better to kind of, so that effort to improve the performance of these data structures ends up benefiting the entire community regardless of the programming language that you're using. So I see this already happening, and I think that more of it is going to happen. On the subject of user interfaces, now this is where a lot of opinion comes in here. So my view, and this is very kind of an egocentric viewpoint, is that I think that the best quality and the most useful user interfaces come from what I call the fire of battle. So you're there, and you've got an itch, and you've got this data, and you've got your boss who wants that, that data wrangled, that data modeled, wants the plot, wants the answer, and you've got a deadline, and you find yourself struggling with the tools that you're using. Either they're too slow, or they're too difficult to use, or you forgot to set strings as factors equals false, and so little things happen, and all of those little paper cuts add up while you're trying to get work done. And over time, you suffer from all that. And if you start actually taking action, say, well, let's improve the tools. Let's examine rather than kind of just suffer from it and say, well, this is the best that we've got, and we've got to get the job done with these tools. To start improving the tools, and if you have that feedback cycle of you're directly impacted by the tools that you're creating. Anytime that you add or you improve your user interface, you make something more composable, you make an API more consistent. Anytime you do that, you make your own life better and the lives of the people around you better. And if you look at work that Hadley has done improving the R, R libraries and kind of creating this ecosystem of packages, if you talk to Hadley, one of his biggest things is consistency. And that consistency comes in when you're writing code and you're sort of moving around, you're making context switches, and just like the number of times that you have to pull up documentation for functions really impacts you in a material way. And so if you have inconsistencies, even small ones, in your programmer user interface, then that adds up to a productivity burden over time. So you need real use cases. You can't be designing in a bubble. And certainly seeing people succeed with tools, that social proof is really critical, particularly when you're trying to convince your boss to use a new tool. It's like, well, can we trust this thing? And be like, well, there's all this social proof that we can accept that. And even 10 years ago, R didn't have quite as much social proof as it does now. Now it's like, well, of course, use R. Same with Python. 10 years ago, it was even worse conversation with Python. It's like, can we even trust interpreted languages? If it's not compiled, clearly it's not safe. And people will use that it doesn't compile as an excuse for not writing tests. And so now I think we know that is really not the right way to think about it. So you got to eat that dog food, as I like to say. And you can learn a lot about a package. And when you're evaluating software that people have built, if you aren't looking at the test suites for software that you're using, you really should, because that's where all the dirty laundry is. In a lot of cases. And so if you open up a test suite and you find that the person building the package hasn't had, we were just hearing from the Carrot folks and how rigorous and intense their unit testing and sort of regression testing process is. And when you're building software like this, it's absolutely critical, not only to validate the correctness and build trust around the project, but also to have the freedom to be able to make changes and improve the quality of the user interface without worrying about whether you're breaking the code. So, well, now let's get specific and talk about a few things, and of course, highly simplified, details about data frames. But the way I think about our data frames is that, if you've looked internally, our data frames are basically a pretty simple data structure built on top of R lists. You have some column names and you have some vectors. You can also have, assign the row names variable, and then you could have dates along the rows, or you could have some other symbol that flows through selections and other computations. But when you say R data frames, what you're talking about is actually a very simple concept. You have the R type system, you have R arrays. It's just a table, and all the value in that table comes from the ecosystem of packages which are built on top of it, which can vary a lot. So if you're just using base R, you really don't have a lot of stuff. I mean, you can read and write files. There's a lot of reshaping and different kind of analytics functions. But to really get a lot of value out of our data frames, you've got to go digging into the CRAN library. So all the value comes from there. Now, of course, there is a lot of great stuff. What I call, a lot of people call the Hadley stack. It's funny thinking of Plier and Reshape 2 now as legacy. 2 years ago, that was, they weren't legacy, and a lot can change in 2 years. Now, of course, there's Datatable and XTS, which are libraries built on top of data frames that bring domain-specific functionality like time series manipulations. In Datatable, you have an extension of data frame which has indexing and the ability to modify and place and various tricks which help with working with larger data sets and getting very fast performance and joins and so forth. It's not all sunshine and roses, as I don't need to tell you. Copy on write bites a lot of people. If you don't sort of pick a set of cohesive tools to use, you can find yourself dealing with the inconsistency and fragmentation problem. And I think the Hadley approach is just have a consistent set of tools and just use that. And so if you stay in kind of Hadley land, so to speak, then you can have a lot better time. A rough edge that I've run into over the years is kind of what I call like the factor string dichotomy. It's like having to pick one or the other, but you have to commit to your choice and then know how that choice affects all of the other code that you write. So just make sure you don't join on factors that have different levels, or you're going to have a bad time. Unless you're using dplyr, or just not with base merge. Another thing with R is the fact that one of the benefits actually is that R's type system is somewhat simplified as compared with, say, a database. So you have one integer type and you have one numeric, floating point type, but it's not a very extensible system. And so for kind of thinking about the future, that's something to think about. dplyr has been an incredible boon for R in terms of thinking about user interfaces and defining that composable table API. And you can't do everything with dplyr, but you can do a lot of useful stuff. So I kind of think of it as like the Trader Joe's of data libraries. Like, it doesn't have everything, but it has pretty much what you need. And I think it's a really great example of what like the decoupled future looks like. And that dplyr was built with multiple backends in mind. So Remind Francois and Hadley built an in-memory, RCPP-based backend to evaluate dplyr expressions, but he designed it with the intent of having SQL backends as well. And so if the data is in a database or the data is in memory, you can write the same code. And not everything works with the SQL backend, but a lot of it does. And I think it's a good model for the future. As a lot of people know, Spark is now building a data frame API into all of their APIs, which I think is really great. And it's a nice, as we've established, it's a nice way to think about tabular data in Spark land. One of the big use cases is the interoperability with Spark SQL. And when you're building data frame expressions with Spark, you're effectively building query plans with the Spark SQL query optimizer, which is actually kind of cool because you can write code which might be really inefficient in R, but you're leaving it to basically a SQL optimizer to decide how to best evaluate those expressions in a fast way. So in some sense, Spark data frames are part of the decoupling sort of trend that's going on. Of course, your execution engine is bound to be Spark. So if you don't want to be tied to Spark, then you don't want to use Spark data frames. But if you're happy being committed to Spark, then of course, go ahead. It's a very new interface, and so it needs it needs users, and the AMP Lab, like Databricks, kind of the Spark developers, need the R community to be telling them what they should be building. Because they're computer scientists, and they aren't really suffering nearly in the way that the R and sort of statistical community has been using DataFrames for years and has a very good sense of like how it should look and feel and what functions are important, and what will create the most value in a short amount of time. Pandas is the project that I've worked the most on, which is kind of interesting to talk about in this discussion because there is a data frame in Pandas, but in some sense, the Pandas data frame, within the scope of the rest of the project, the data structures themselves are not that interesting. I mean, they're important. So there's multiple data structures. The data frame is the one that most people use. But you look at, okay, it's a table. It's got columns. It's got arrays inside. And if you go back to like Pandas 0.2 or 0.3, and maybe there's some people in the room that used Pandas way back then, it was a much simpler library. And now all of a sudden it's 200,000 lines of code. And on GitHub, where you know that they number issues and pull requests in sequential order, I looked today, and it's about to cross into the 10,000s. So it's like 3,500 pull requests and nearly 7,000 issues. So there's more than just data structures there. And it's kind of the thing about Pandas is that it wasn't only just the table; it was the fact that you needed to build kind of the whole ecosystem of tools. So if you look at R, you've got a lot of different packages which implement different functionality that involves data frames. And so the data frames themselves are very simple. In Pandas, it's kind of this like walled garden approach or batteries included approach where you have a really sort of fat library with a lot of stuff, all the I/O stuff, all of the data wrangling, all of the group by, like transformation. There's even a bunch of plotting things in there. So it's this really expansive library, which is both a good and a bad thing. And there's two kind of really distinct qualities is that because it was built in a financial setting, it's become very successful in financial services because people view it as one of the best time series libraries. And if you use Pandas, what I will describe in a very technical way is hierarchical access labeling, which is something that doesn't really exist in R. It is very powerful, but also makes the library complex in some ways. So it's both a good and a bad thing. So more about that. I mean, I've got a book that's about 50% about Pandas, so you can learn all about that in there. So at the power comes some complexity that the access labeling stuff in Pandas can create a bad experience sometimes for people coming from R who are expecting to have like a very kind of vanilla table data structure. The fact that Pandas was also built with NumPy compatibility in mind also has led to rigidity in that the data is stored in NumPy arrays. That means we don't have complete control over the type system. There's missing data handling issues as a result. Strings are an issue, little things. If we freed ourselves of dependency on NumPy, we could go and fix some of these problems. So the next-gen Pandas for Python programmers is certainly something that is needed. Julia has data frames, and I know that there are some Julia developers here. I saw Harlan Harris, I don't know if he's around here, but he and some other folks spearheaded DataFrames.jl, which I see now has had over 60 contributors. And if you compare Julia's data frames with R and Pandas data frames, it's a lot more like R data frames. And that kind of goes in line with the broader Julia Stats initiative to create a statistical computing environment in Julia. It's still, as Julia as a language has only been out there for a few years, data frames in Julia are still our earlier stage library. So things like if you want a SQL interface to Julia data frames, I don't know if it's found in the library, it might be elsewhere. You're dealing with something that's a lot newer, but there's also a lot of exciting opportunity there with the broader benefits of the Julia language on your side. So there's data frames in other languages, of course. Adam Klein, who's one of my colleagues from AQR, worked with for several years. I guess I sort of infected him with the sort of Pandas, data frames, all the things. And he's jumped from a couple of financial companies and has been building data frames everywhere he goes, which is great. So now we have data frames in Scala and in F#. I also wanted to throw a shout out to the Graph Lab, who are now Dado folks who've built a really amazing and scalable data frame. It does have a licensing issue, which will be interesting to see how that leads to community development or lack thereof. But it really is an amazing piece of software engineering. And there have even been data frames built in Haskell and Go and other languages. So I'm running out of time, but a couple of things that I wanted to say is that the future is JSON-like. It is semi-structured and not structured. So we need to think about our data frames and how we can augment them to support nested types. So to have fields that are not simply numbers or strings, but could be sequences or maps or structs. And that would enable an R-like or a data frame-like structure to also account for the data of the web, which is JSON, with the types, of course. I think it would be really great if we could put our heads together, we, the people of the world, and build a community standard data frame library that we all use, rather than having parallel implementations of all the same things. That will require some compromises and design work. But I think it's a greater part of the great decoupling, which I'm very excited to see happen. So that's all I've got. Thank you.